Hello and welcome to the second part of exercise series 9. So now we're going to have a look at full function analysis. So we're going to write down the exercise I recommend you to make at home. So recommended for home would be exercise C, F, G, H, and O. We're going to make quite a couple together. I think I'll split it up in a couple of videos. So because these exercises take quite some time, I'm going to take my time explaining each of the steps. But first and foremost, I want to draw your attention to, the last 2 pages of the theory overview where I've put a full workflow of how to do a full function analysis. Many of these steps we've already seen in different exercise sessions. It's just now everything comes together. The only thing that's new now is a second order derivative. We're going to have a look at that. Basically, it just means you take a derivative of your derivative. Okay, that being said, let's jump right into it and let's have a look at question A. And I know this is a rather straightforward function. If you remember your function transformations, you could draw this immediately. But it's a good exercise to really run through the steps one, and afterwards I'm going to make a couple of more challenging ones as well. So don't worry. So first things first. What do we need to define is, what's our domain that we're working in? So that's dot 1. And for this function, no value of x really gives us a problem. So we can just say the domain of this function is just R. Okay, then we'll have a look at our roots of our function. And our roots of our function, they happen when x to the power 4 is equal to 0, or in other words, when x is equal to 0. Careful, this is a 4-time root, right? This happens 4 times. And remember what I said about even roots, basically it means it does something to the sign, which we'll look at in step 4. Then at step 3, let's have a look if this thing has a horizontal asymptote, so approaching infinity. No, not really. So horizontal asymptote, no. Does it have a vertical asymptote? No, there is not really a denominator to talk about, so no vertical asymptote. Let's have a look if this is an oblique asymptote. Also, no. Okay, then let's continue. Step 4, we need to combine all of this information and do an investigation of the sign, right? This is information we're going to just keep in the back of our minds for now, and we're going to use all of that later when we need to sketch the function. So as per usual, we say this is x, this is our function, fx, or you could just write x to the power of 4. We know that it's 0 at x is 0. And what else do we know about the function? Well, we know that it's to the power of 4. It always gives us positive numbers, right? So it's going to just be positive on the left side and positive on the right side. And here you can see, the sign doesn't change. This is mainly because of the reason that this is a 4 double. Well, this is a root that gets repeated 4 times. Okay. So far we have already done this. Okay, then let's look at the next part. So let's find the derivative of this function. So f accent of x. Dropping the 4, then 4 minus 1 gives us 4 times x to the power of 3. Okay, so now we have that. Then we're interested in, first finding the roots of this. What are the roots of this new function that we find? So what's the roots of the derivative? So as you've probably already seen in the lecture, the roots of your first derivative, they will tell you something about local extremum or extremum of your function. Okay, so basically it means that, when it's equal to 0, it means that your function needs to become flat, right? And there are a couple of ways you can do it. You can do it like this, you can do it like this, or it could do it like this. And our goal is to basically distinguish between those. And here, let me rewrite it a little bit. Mainly, I want to do it like this. So you see here our derivative, which remember is our tangent line. It's going to be flat, it's going to be flat, and over here it's going to be flat as well. Okay, let's remove that. So we're interested in where this is equal to 0. So where is 4x to the power of 3 equal to 0? Well, it's going to be 0 at x is equal to 0. Okay, that means we can now investigate the sign of this function as well. F accent of x, here at 0, we know that it's going to be 0. This is a third power function, so we know that it goes from negative, it changes at 0, and it becomes positive again. Okay, so what does this mean for our original function? Because, well, remember, a first order derivative will tell you something about how the tangent looks, right? So it will basically tell you whether the function is ascending or descending. So if the first order derivative is negative, it means our function is descending, right? It means that if we took a little step to the right with your delta x or h, remember the function of the limit, well, that little step is going to result with a smaller value, right? So it means our function is descending. Then here we get at 0, and then 0, and it just happens to be that it's 0 here for the original function as well, so we can write 0 over here as well. It's not always the case, and then it rises. Okay, so here you can already kind of see kind of a behavior of the function, right? You see that it goes down, 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 until it hits a certain point, and it goes back up. Okay, this is going to tell us something already very interesting about the shape. And in this case, it's probably very obvious, but try to keep your head with it and try really to see what I'm saying here. You see the function goes up, down, and then it goes up again. Not necessarily like this, right? It could also go down and then up again like this. This is something we'll have to determine later. But all we know is that the function goes down and then up. It could also be like this, right? Okay. So that being said, we now get to step 7. So step 7, what do we need to do there? We need to find our second derivative. And this is a first for you guys, but you'll see it just follows the logic of everything else. It just means f double accent, or in other words, you just say, you take f of x, the derivative of that, you take the derivative of that again, so basically you get f double accent of x, which means the second order derivative is just the derivative of the derivative. So we can rewrite it, you get 3 times 4 to the power of x to the power of 3 minus 1, or in other words, 12 times x to the power squared. Okay, now let's apply the extremum test. And the extremum test is basically looking at the roots of our first order derivative. Remembering this was the root of our first order derivative. And most of the time, if we plug this into our second order derivative, it will give us some information. Not always. So let's plug this in over here. And what do we find? Well, we find that f double accent of x, no, not of x, well, we evaluated at 0, is again 0. And if you read, well, my theory overview, it's, well, going to tell you that this is kind of, it doesn't really tell you something, because we're interested in the roots that are not the roots of our second order derivative. So, meaning in this case, there are none. There will be an exercise coming up where, well, this will tell you something. Basically, if this is greater than 0 or smaller than 0, it will tell you something about the point that you have reached over there. Okay, this actually tells us that we need to investigate this further. It means that we don't really have a conclusion just yet, right? So in this case, well, let's move on to point 9. So we'll say 8 is inconclusive. Then we go to 9, and there we say, well, we're interested in finding the roots of f double accent, right? The second order derivative. We've already done that. We know that the second order derivative of x is equal to 0 at x is 0, right? Okay. Well, what can we do now? Well, if this was greater than 0, it would have told us something about, well, this point over here. Now it hasn't done that. Okay, so this is a trick you can see, and I think the professor talks about it in the lecture as well. It's not always possible, but basically what you can do is another kind of extremum test by taking more ordered derivatives. So you can say, well, this is not really the final amount of derivatives we can take until we basically lose all the information in the function. Well, when do we lose all the information in the function? Well, basically when we have nothing left, when the function is just equal to 0. So what we could do, we could say, well, the third order derivative, denoted like this, or often denoted like this as well, is equal to, so we had 12x squared would be 24x. Well, this still has some information for us because we still have 24 times x. This is still something. So we'll take our first power derivative. We just get 24 then. And if we were to derive it one more time, basically then it will tell you that you have, well, that if you derive it one more time, you will have lost all your information. So what do we look at now? Well, basically you look at whether this thing is even or uneven. And this is not always going to work, this trick, but I wanted to show you once how it worked. In general, there is already a lot of information here because we're kind of lucky, but I'm going to draw your attention to that later. So this is even or uneven. So for us, it's even. And when it's even, it means that we either have a minimum or a maximum, right? At the point that we're investigating, which in this case is the point that we're investigating, is where x is 0, because, well, our point 8 was inconclusive. And in this case, well, it is even, and if we keep deriving it, well, the last function that we have that still has some information for us is greater than 0. So what does it tell us? It tells us if it's even and greater than 0, it means that we have a minimum. Okay. If it was smaller than 0, you would have had a maximum. So even and smaller than 0, you have a maximum. Now, if it were uneven, it means you have a point of inflection. This is something will come up in other points, but basically remember I told you that it could be equal to 0 in a couple of ways, right? Your first order derivative, it could look like this, it could look like this, or it could kind of look like this, right? So this means like this. It means that this point over here is going to be also where the derivative is equal to 0, but it's going to be just a part where the function kind of changes its, well, it kind of changes its shape a little bit, right? It changes here, it changes its shape. So, but for this, let's have a look a little bit further. Okay, so now that we have this, well, let's have a look at what our second derivative will tell us. So our second derivative, what it will tell us, we'll make a sign table for that as well. So you say x, second order derivative, and then we evaluate its sign. So we say, well, here at 0, we know that it's equal to 0. Then before that, we know that it is positive. And after 0, we know that it's positive as well. So what does this tell us? Well, it tells us the way actually the function is going up or down. Is it going up or down? Is it increasing in speed by going up, or is it decreasing in speed by going up? If it were to increase in speed by going up, it would look something like this, right? If it were decreasing in, so you can, what do I mean with increasing in speed? Well, you see that the tangent lines only become steeper and steeper and steeper, right? But it could also decrease, and that means that the tangent lines will become less and less steep as we move along in our values, right? Okay, so this tells us if it's positive, it means that it's increasing, which means that our function will look we will have this shape, right? It will have this shape and we'll combine it with later. So basically it means like this. Now, this is called convex. It means if your function is convex, and if it were negative, you would get a function that looks like this, which is concave. But there's one very simple trick to remember what shape it would have. Well, the easy way to remember it, well, a positive sign is a positive feeling, so you get like a little smiley. If a negative sign is a negative feeling, so you get a little frowny face. This is a very good way of remembering what you need to fill in there. Okay, so now why did I do all of this? Well, sometimes you will find points of inflection that are, well, at other points, right? A function could change between these two. So imagine we find plus, minus, it will change its shape. How would that, for example, look? Well, the function keeps first and foremost increasing, 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 becoming steeper and steeper and steeper. And then afterwards, it stops becoming steeper and it kind of looks like this then. So you see, well, first our function kind of follows like this pattern and then it becomes less and less steep. So here somewhere there's going to be a changeover between these things. And this is going to happen where we have a root in the second order derivative. Okay, all of that being said, sometimes we're lucky. In this case we are, because the only roots, well, that this thing has are also the roots that we have in our first order derivative, right? These two line up. And you kind of, in this case, we can make an inquiry very carefully about what our function is going to look like. So we need to combine something that goes, well, that goes down, and it goes down in a certain way, right? It goes down following this pattern. Imagine we just cut it in half, and then we add an arrow to it. So it kind of means that we're going down, and we're going down in this way. Then we hit, well, somewhat of an extremum, and then we move up again. So what does this tell us? This tells us that we are reaching a minimum over here. So this is exactly the same conclusion. So you can just bring this information together. So in this case, well, the arrow is going up. We have a shape like this, cut it in half. It means that it's going up like this, right? Okay, so in that case, we need to bring all of this information together. So, and there are a couple of ways to do it. I don't tell you that you need to do this, but it's always a good idea to make a kind of an overview of all of the information you have. So first things first, well, we know that value for x is equal to 0. Our function itself is going to be 0 there, and it's going to be positive. So it's going to have a positive value. Before 0, well, we know a couple of other things. Well, we know that our function is, our first order derivative is going to be negative. So we know that our function is descending on this side of our root. Then here at 0, it's going to be 0 again. And we're going to hit a minimum there, and then it's going to go up again. And then we know something about our second order derivative as well. Well, we first know that it's positive, then it's 0, and then it's positive again. So we know that we have a shape kind of like this. Okay, now we need to bring all of that information together, and let's try that once. So I have an axis over here. Let me pick a different color. And so first things what we know is we need to hit over here, right? We know that our function is going to be 0 at 0, right? We put it over here. The other thing we know is that our function is going to operate within the positive quadrant. So that means our function is not going to be here, right? Okay, what else can we look at? Well, some other information that we have is that first our function is going to descend, then it's going to hit a minimum over here, and then it's going to increase again, right? And there's only a couple of ways that it can do that. Basically, it could go up like this. Well, there is actually only one way to do it in this case. So basically it would decrease, decrease, decrease in the positive area, and then hit its root, and then it moves back up. So here you can kind of see the shape that I was talking about earlier, right? You see it goes down, 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 down in a convex way, and then it goes up also in a convex way, right? So really follow those smileys, right? So you can see it goes down, and then it goes up again. And once you have done, well, you have done all of the steps of a full function analysis. So this would be step 10. Of course, there are many other challenges that could reside in this, right? How can we make an exercise like this harder? Well, basically make a less straightforward domain. Or other ways is basically introduce some asymptotes. We could also make it harder like that. Make the first order derivative harder to calculate and have less obvious roots, right? And then also the second order derivative, like what's that going to do? Maybe make that a little bit more difficult. This is a very straightforward example, and we're going to make a couple more. So the first one we're going to make on top, and this is going to be the last one I make here in this video, and then I'm going to move on to a next video because otherwise I think it's going to become too heavy and too many things to see in one video. So this one is still going to be kind of straightforward. So we have a function, exercise t. And we have here 1 over 3 x to the power of 3 minus 1 over 2 x squared plus 1 over 4x minus 3 over 8. Okay, so first things first, let's consider the domain. So we say 1 domain. Are there values of x that are going to give us a problem? Well, Not really, right? We can fill in whatever we want. So we say domain, perfect, it's just going to be R, all the real numbers. Then, now we need to find the roots of this thing. But this is a kind of a messy way of looking at it, of finding a root, right? Because, well, we have all those fractions. So maybe we can rewrite it a little bit. So let's try and get rid of those fractions. And basically what we're going to do is we're going to multiply everything times 24. How do I know? Well, to do times 24, well, if you consider all of these numbers, what's its least common multiple? Well, it would be 24. So that means you can simplify all these fractions by just multiplying by 24. So in other words, what do you get? You get, well, 1 over 24 because, well, we did times 24, so we need to take that out again. So we get, in this case, 8x to the power of 3 minus 12x squared plus 6x minus 9. Okay, and now we get to the point why I actually selected this exercise. It is great for many other things, but I think it's a bit mean to just expect you to find it at home. But sometimes Horner doesn't work, as you might know, right? And then roots become a lot harder to find. In the exam, we'll make sure that it will not become impossible to find these, but in this case, well, I'm going to tell you what you need to do. So to simplify this a little bit, well, what can we bring out? Well, we could bring out 2x minus 3, meaning that our root is not going to be at a nice integer, it's going to be at x is equal to 3 over 2, right? And we're going to do that. We're going to divide this entire thing by that to see what happens if we bring that out. And then you will see, well, we can do a long division for that, just as a quick refresher on how these things work. So we say 2x minus 3, you get here 8x to the power of 3 minus 12x squared plus 6x minus 9. Okay, that fits in there for x squared times, so you get 8x to the power of 3 minus 12x squared. Okay, that works out very neatly. We get 0 over here. Let's drop this. We get 6x minus 9. So we say plus 3. And this is again 6x minus 9. And these things neatly cancel each other out. So in that way, you can easily simplify it. So in other words, what do we have here? Well, this thing is just 2x minus 3 times 4x squared plus 3. Okay, so again, remember in the exam, you can just try Horner. Normally it should work, but sometimes it's not that neat. Reality is not that neat, and then you can look at the computer and the computer will tell you where the roots are. But for now, let's consider we found this all by ourselves and let's continue working with this, because the other parts of the exercise, like this is a bit of an obstruction, but the other parts of the exercise has some very neat examples as well. So okay, I'm going to remove this. Okay, so now that we have that, well, we can consider our roots. So first things first, we know that we have a root at x is equal to 3 over 2, right? I found this by saying, maybe let's add another step. 2x minus 3 is equal to 0, or in other words, x is equal to 3 over 2. So that tells us this, and this, does that have a root? Think about that for a bit. I'm sure you have your answer ready now, but no, this does not have any roots, right? Because, well, for x squared, there is no way that that can become negative, because x squared can only give you positive numbers. Okay, so now that we know that, let's continue a bit with our exercise. We'll move on to step number 3. I'll write it over here to save a bit of space. So step number 3, we're interested in first our vertical asymptotes. Are there any? Well, no, not really. We don't run the risk of dividing by 0 anywhere. So our domain was just R, so no problem. So no vertical asymptotes. Are there any horizontal asymptotes? Again, no, they're not. Are there any oblique asymptotes? Well, let's check. Again, no. You cannot, if you're not sure, the only thing you need to do is, well, check the limit, right? The limit of x going to plus minus infinity of your function over x, and then see what you get. Then you get your m value. Well, and if this is already nothing, then you can look at your n value, and if you have only an n value, it also means you just have an horizontal asymptote, right? Okay. So these, all 3 of them, they do not exist. Okay, let's continue then. And then let's make a brief function analysis. So we say this is x. I'm just going to say our function f of x, it's much easier than rewriting all of that. And well, we found that it only has one root. It namely has a root at 3/2. And it's going to be 0 over there. Okay, let's see. Is it going to be positive or negative? Well, we know that if we fill in 0, which is smaller than 3/2, we get 0 minus 0 plus 0 minus 3/8. So that's a negative number on this side. We breach the x-axis, we change the sign, and it becomes positive. Okay, so this is our first information we have about the function. Then let's go to point 5. Now we need to find the derivative of this thing. And here, neat things fall away. Of course, you can take the derivative of this thing over here, but actually you'll see that it's much easier to take the derivative of that. Why is that the case? Well, what do you get for the first part? You get just 1/3 times 3 times x, 3 minus 1, or in other words, just 2. And you see, well, that fraction neatly cancels out with the exponent that came down. So in this case, it's just x squared. And we see that just the same thing happens with x squared over here. Basically, the 2 comes down, and what are we left with? With just minus x. This becomes plus 1/4, and minus 3/8. Deriving that, it just becomes 0. Okay, so now we have our first order derivative. Let's see where that one has roots. So 0.6, and we'll say, where is f of x equal to 0? Or in other words, where is x squared minus x plus 1/4 equal to 0? Let's calculate the discriminant of it. The discriminant is minus 1 squared, so just 1, minus 4 times a is 1, c is 1/4, so in other words, this is equal to 0. Okay, so that means that we have a double root at 1/2 by just filling in the formula we have been doing the entire year. Okay, now that we know that, we can make a small investigation into the sign of and how our function rises and falls. It's okay, we have x, our first order derivative, and then we know that our first order derivative is going to be equal to 0 at 1/2. Okay, let's investigate its sign. Well, you already know that it's an x squared function, so you know because there's no negative in front of the x squared that it should look like a cup. So we know that it's going to be positive and positive. What does this mean for our original function? Well, it means that up until the point 1/2, our function is going to rise, it's going to do something, and then it's going to rise again. Okay, and so here I want to draw your attention to something a little bit. Here, over here, you could see it was going down and it was going up, right? And that was a typical behavior for a minimum. If it were to go up and then it were to go down, well, that would look typical behavior of a maximum in your function. But here we have something quite different. We see that it rises, it flattens out, and then it rises again. Well, I'll let you think about what that means, but it gives us already a very strong indication to what this point 1/2 is. Okay, then let's have a look. We'll do 7 and calculate our second order derivative. Our second order derivative is just deriving the first order derivative. So in other words, what we get 2x minus 1. Okay, now let's apply the extremum test to that, right? So 8 f double accent at 1/2. Unfortunately, again, it's equal to 0. So the test fails and it doesn't even tell it. It doesn't tell us anything. So again, we could follow the logic that I did before. So we keep deriving it as long as we don't have any information left in the function. So we say, okay, let's derive it one more time. And we say, okay, the third power derivative, that's going to be the last one that has information because that's equal to 2, right? Because if we derive this one more time, we just have 0 because it's a constant. Now, let me draw your attention again to what I said over here. When this is uneven, we know something about this point. Because in this case, if it were even and your value was greater than 0, you had a minimum. If it was smaller than 0, you had a maximum. But now it's uneven, which means, because this is uneven, you have an inflection point at that point. Okay, but we could have already seen this actually. How could we have seen this? Well, it means that our function rises, 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 flattens out, and it rises, rises, rises again, right? It doesn't necessarily have to do it this way. There are many other ways you could do it, but yeah, you could but in general, when you see this, it will kind of look like this. Okay, so that's one way of looking at it, right? But you could have just seen it immediately over here of this as well. So this second test, it can help you, but it doesn't always necessarily help you, or it's not always necessary as well. What is necessary is the next part, and that you find the roots of your second order derivative. So in this case, we'll say f of x is equal to 0 when 2x minus 1 is equal to 0, or in other words, this is only true when x is equal to 1 over 2. Okay, we already knew this, of course, but it's a good way to just run through all of the steps and get the habit of doing that. Okay, let's investigate what this means for the sign. So of this function, we get x, f double x, cent of x, so the second order derivative, at 1 over 2. Well, we know there it's going to be 0, and then now let's have a look at what the sign will do. Well, first it becomes negative, and then it's going to become positive. So what does this mean for our original function? So it means that, well, our function is going to be concave first, change, and then it's going to be convex. Okay, now let's bring all of this information together. So we get a big table, we'll make a big table, say x, our original function. Well, we have a point of interest here at 3 over 2, and we also have a point of interest at 1 over 2. So our original function over here is just negative, it's going to be 0, and then it becomes positive. Our first order derivative, what do we know? Well, it's going to be 0 over here, and then it's going to be positive, positive, positive. And our second order derivative over here, it's going to tell us that first we have a concave function, then we have a change, and then it's going to be convex. So let's combine these arrows for first. So you have something like this, let's chop it in half, so that means you have something like that, let's add an arrow to it, and we kind of see that it needs to rise in this way. Then we have an arrow that goes up, we have something this shape, let's cut it in half, we have something that goes up like this, right? And it rises like that, as such. Okay, so now that we know all of this about our function, well, we can try and sketch it again, right? And of course you can continue and you can say, well, the function keeps respecting this general shape. Okay, let's draw it once. So first things what we know is, well, here at the point 3 over 2, our function is going to be 0. Now let me pick a different color so it's a bit clearer. Here our function is going to be 0. Another thing that we know is at another special point, namely at 1 over 2, something is going to happen. Okay, so now let's ask ourselves the question, well, what's this going to be? So let's have a look here at our function. And we learned that here at 1 over 2, well, we had an inflection point, right? It kept rising, it flattened out, and then it rose up again, right? And it would change its shape exactly at that part as well. So this means, well, this 1 over 2, it's smaller than 3 over 2. We know that our function is negative there, so it means that we're here below the x-axis. We are operating here. Of course, you can just fill it in and find the point. And if you were to do that, you would get that it's at minus 1 over 3, and you would find that you have a point over here where something happens. You don't necessarily have to find this point, only when we tell you, well, find the extreme point, you can calculate it. But in general, what's really important is that you know it's going to be on the negative side of the x-axis. And with that, I mean like underneath the x-axis, so over here, right? So don't get confused with what I just said. So in that case, well, let's see what our arrows do. First, it goes up, hits that point of 1 over 2. There it becomes flat for a bit, and then it moves up again. And we still need to hit this point over here. And there are only a couple of ways that I could do it. Well, it rises, 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 rises with this general shape. So in general, it's concave. and then it changes its sign, it flattens out, so really be careful here, it needs to flatten out, and then it moves up and it changes its shape like this, and it continues. Sorry, it's a bit a wonky line. It continues like this. So this is in general our full analysis of the function. So here we have our inflection point, here we have our root, and here we have the general behavior of the function, where the function rises like this, and then it continues to rise, but now like this, right? You see how the arrows point. Okay, so I think that's enough for the first video. We're gonna make a couple more, but for those, I'll see you in the next video. Of course, the exercise is gonna become increasingly more challenging, but we'll make sure that you have seen a bit of everything. Okay, see you there.